So we've already had one flawed recording in this class. I have another. Okay, so as I was saying before I started recording, we have a lot of stuff here. So my plan is to spread this out. So I might probably only go through a few pages worth today, depending on how things go. Now, based on my usual pace of going through notes, it could very well happen that between today and Monday, I'm able to finish it. Now, for the following Wednesday, so April 13th, I will already not be having my other class of PDEs. So if I end up getting through this whole section in 2 class periods, then Wednesday will just be a no class for Dr. Lambert's day. So all the way around. So I'll be able to let you know on Monday. Now I bet it all here thinking, okay, let's just not ask questions.
Or email them later.
Well, yeah, it's always that. So.
There we go.
Crafty. It is hot in here.
Yes.
Well, supposedly the thermostats in my office, at one in my inner room, one in my outer room, might affect the temperature of these classrooms or certain ones.
Yeah.
But I never know which. I haven't touched them in a long time, but because I'm worried about causing something like this to happen. I don't know if it'll help to open the windows.
We can try.
Yeah, if we can give that a shot.
It's just 2 of us. You might just take your mask off.
What?
Yeah.
I said you have your mask
You can-
on. I
Oh,
don't know.
okay. All right.
It's up to you.
Okay.
Or we can put
So.
ours on if you want.
All right. Well, I've implied permissions from the 2 students in this room.
Yeah. And we already see you.
Well, we
My
do
mask.
research with you anyway.
Yeah.
That's true, and
Not instructional setting.
with only 2 here, we have distancing. So
Yeah.
okay, that'll help.
Oh, this is broke.
Okay. Oh, okay. There's a little bit of a breeze coming in. So
Yeah, that's nice.
yeah.
Luckily, we are at some height.
Okay. Now, the importance of convergence analysis for time-stepping methods for ODEs, like the ones we've been seeing, Euler's method, Rowan-Cutter methods, multi-step methods, is to have some idea about when they actually work. Under what circumstances will they actually produce the correct solution? Because if under certain circumstances a method will not converge, and we don't want to use it in such a way. Also, as far as the measuring performance, like we can know something about the error in a certain method as a function of, say, the parameter h, the time step size, then we can use that to select an appropriate value of h. And it's something, you can think of it as a Goldilocks problem. H can be too large, too small, or just right. If it is too large, your solution is not as accurate as you would like. If it's too small, you'll get enough accuracy, but you lose efficiency. So you want to try to find where it's just right. And this gets into something called adaptive type-stepping methods, which admittedly I won't be covering in this class. There's a section on it in the text. But this kind of error analysis, convergence analysis can be helpful towards developing better performing methods in terms of finding the right balance between the need for accuracy and efficiency. Having this kind of theory gives confidence that the methods will work. And because when methods like this are implemented in mathematical software, there are people who shell out real money for this kind of software. They want to know that it's going to work. They need to have that rock solid faith. And this kind of theory can give them that. So this is for anybody who thinks there's no point in an applied math class or a computational math class and steps of theory. Yeah, we do need it. Because what I found, and I step on the soapbox for a minute, sorry. Numerical methods are used in a wide variety of scientific and engineering disciplines. I had some dealings, for example, with people in the petroleum engineering field. who use these methods. And they have a decent working knowledge of these methods. They can code them up. They know the basics. But what I found was that they didn't really know them in depth, not like a numerical analysis person would. And that would lead them to use them in not the most optimal way. Like doing something that is wildly inefficient, for example, or maybe using a method that isn't going to perform and produce a correct solution in the case that you're wanting because of the complexities of a particular problem at hand. That kind of expertise is needed. And that's why it's good that certain, there is some back and forth between academia and industry, at least in certain fields. Petroleum engineering is one of those fields. But still, there isn't really enough penetration into government or industrial research of the kind of expertise that is needed to use such methods optimally. Okay, so what is convergence analysis all about? I've shown you a very little bit of convergence analysis to date, and that was with the simplest time-stepping method of all, Euler's method. I produced a proof at the beginning of this chapter that as h goes to 0, that the error, the computed solution minus the exact solution at a certain time, goes to 0. So in other words, Euler's method is said to be convergent. Now, that was a fairly tedious proof for such a simple time-stepping method, and it would be a whole lot worse for more elaborate time-stepping methods. So what we're going to do is break the analysis down into bite-sized chunks and define certain concepts that apply to all time-stepping methods of the kinds we've been looking at, to have a uniform framework for convergence analysis. And this leads to other properties that a method can have. Also, the most important thing is to know that a method is convergent. But we'll also learn what it means for a time-stepping method to be consistent or stable, and how do you show that a method is consistent or stable. And those two concepts pave the way for establishing convergence. So, so here's some things I need to define in order to discuss convergence analysis in more general terms. First, very important, is local truncation error. So that, in a nutshell, is how much error is incurred in one time step. So if you assume everything is exact up to that point, you use your time-stepping method for one time step. Of course, there's going to be some error, and you want to be able to quantify that, and that is local truncation error. The way you obtain local truncation error, this is the key part right here. You substitute the exact solution into the numerical method. The idea is this. The numerical solution satisfies the numerical method exactly. The exact solution satisfies the exact ODE exactly. But if you substituted if you mix and matched, like substituting the computed solution into the ODE, or going the other way, the exact solution into the numerical method, they will not satisfy those respective equations exactly. There's going to be something left over, and that's your error. So which way do you go? Well, it doesn't really make sense to substitute the computed or numerical solution into the ODE because it's not a function of t. It's just a set of values. It's a discrete entity. Whereas y of t, the exact solution, is a continuous function, then you can evaluate at whatever points you want to get a discrete set. So substituting the exact solution at selected times into the numerical method is something you can do. And using Taylor expansion, for instance, we can figure out what that leftover part is, and that is a local truncation error. So for a formal definition of local truncation error, at least for Euler's method, the idea is that the numerical method is written in such a way as to mirror the ODE. Because the ODE is, oh, this is unfortunate. I I mean, the ODE is not written here, so I'm going to fill it in just so I can compare. Okay. So tau n, tau is often used to refer to local truncation error. So it's a symbol that's used in many texts. So that's what we see here. And it depends on the time step size h. So what we have here, this is an approximation of y prime. So the ODE is y prime equals f, or in other words, y prime minus f is equal to 0. So that's how I define local truncation error. Approximation of y prime minus f. What I can do here is, for Euler's method, I can Taylor expand y tn plus 1 around the center tn. And that gives me this. And then, when I simplify this, notice we have a common factor of h up above and below that we can cancel. Well, y prime is equal to f. So this term and this term cancel. What's left? Just this term. Don't forget to divide by h. So h over 2y double prime at an unknown point. That is the local truncation error of Euler's method. And we saw that last time from a proof I did. I just didn't call it local truncation error. But now we have this concept defined. And it is order h. So it's proportional to h to the first power. So we're seeing first order accuracy. And soon I will give you a formal definition of local truncation error for general time-stepping methods. But the idea is you write a numerical method in a way that mirrors the ODE. So the ODE is y prime equals f. Local truncation error is approximation of y prime minus whatever you're doing for time derivative, your approximation of f. Okay. Now, we want the local truncation error to go to 0 as h goes to 0. Now, these are concepts of consistency. So, a consistent method is a method that has that property. In other words, as h goes to 0, the numerical method, when written this way, converges to the ODE. So that's the idea. When you say consistent, you think in terms of something being consistent with something else. In this case, the numerical method needs to be consistent with the ODE. Now, consistency is not convergence. Consistency is necessary for convergence, but it is not sufficient. But consistency is easier to show directly. To complete the picture, to get from consistency to convergence, what you need is stability. And here I'll give an intuitive definition. I'll give a formal definition a little later, one for one-step methods and one for multi-step methods. That the idea behind a method being stable is a small change in the initial data should not lead to an unduly large change in the solution. It's kind of like the notion of well-posedness for the ODE itself. So the underlying problem, so that I'm not talking about numerical methods here. The problem that you're modeling with the numerical method is well posed if the solution exists, the solution is unique, and the solution depends continuously on the data. In other words, a slight change in the problem should not lead to a very large change in the solution. And yes, it is a nebulous concept, but it's something I'll formalize later. So this is related to that, the numerical method should not exhibit that kind of behavior either. So if the problem itself is well posed, then the numerical method should also behave in that way. That a small change to input of the numerical method should not lead to a large change in the solution. And you're going to have small changes in input all the time. Why? Because there's error involved. There is always error. If you have some tiny round-off error, and your numerical method is going to cause that to blow up into something that wrecks your solution, then that's not a good numerical method. You should not use it. So then what we'll see is that if a method is consistent and stable, then that leads to convergence. You can think of it this way. Like I said, consistency is about local truncation error, the error committed during one time step. A stable method ensures, stability of a method ensures that whatever errors occurred over individual time steps does not accumulate in such a way as to have a really large error after time stepping for a while. That even though there is error in every time step, it doesn't get out of hand, no matter how many time steps you take. So that's what stability is giving you. Because convergence happens when all of that accumulated error still goes to 0 as h goes to 0. Because as h is going to 0, what's happening? If you're time stepping from time A to time B, you let h go to 0, what's happening? You're taking more time steps, more opportunity to accumulate error. But if that error can be bounded, no matter how many time steps you take, then you're on your way to having a convergent method. So now, to be more precise about these concepts, I'm going to focus, for now, only on one-step methods. They will deal with multi-step methods later. Now, here I have a general form of a one-step method. Y plus 1 equals yn plus h times some function. It could be a very simple or complicated function. It depends on the time that you're at, tn, your previous solution, yn, the solution you're trying to get, yn plus 1, and then your step size h. Now, what I found kind of troubling was that I've seen this form of one-step method in certain other books, but for some reason they would not include yn plus 1. It would only depend on tn, yn, and h. And like, well, that's too limiting. You can't describe an implicit method that way. Implicit methods involve yn and yn plus 1. So I broadened it to include both. So for a simplest case, again, Euler's method, the function in question would just be f, evaluated at tn, yn. Whereas if this was backward Euler, the implicit counterpart, I'd have f of tn plus h and yn plus 1. So that's an example of this function phi. So now I'm ready to define local truncation error for a general one-step method. It actually has a nice simple definition. It's just this. So your approximation of dy dt minus your function phi. So you just work out what this is, and what you might do is then do some Taylor expansion to get a handle on how large it can get. But this is all you need to have an expression for local truncation error. Now, if this local truncation error goes to 0, as h goes to 0, the method is consistent. Well, let's see what happens as h goes to 0. Well, this converges to y prime at time tn. And then, as h is going to 0, then we have this. So, we need this to go to 0, so h goes to 0, but y prime is equal to f. So, as h goes to 0, this needs to converge to f of tn, y, tn. So in other words, this is how you know that a one-step method is consistent. That you figure out where your function phi is for your method, and you evaluate it at this point. If you get f of ty, you're done. Method is convergent. The method is consistent, not convergent. Consistent. Dang it. What did I say 2 minutes ago? Consistency is not convergence. I love myself sometimes.
Hey, it's halfway there, right?
Literally, yes.
One step there.
Yeah. Okay. All right, I think what next is an example. Yes, an example. Okay. Midpoint method. Now, with the midpoint method, you evaluate your time derivative at the midpoint in time between Tn and Tn plus 1. So you take half a time step, Tn plus h over 2. So then what you need here is an approximation of y at time Tn plus h over 2. Well, the way you can get that is take half a time step using forward Euler. And that's what this gives you. So that's just the definition of the method. So from this, I can write down what the function phi is. So it's just this. Like, whatever's multiplying h in this term. So one-step method is always y plus 1 equals yn plus h times something. The something is phi. In this case, it doesn't depend on yn plus 1 because this is an explicit method. So now, to check consistency, all we got to do is go to this, set h equals 0. And sure enough, it just reduces immediately to f of t and yn. So it's done. It's consistent. Nothing to it. Here's another. This is an implicit method, trapezoidal method. You may recall there were two trapezoidal methods I showed you. There's an explicit and implicit variety. Here we'll just look at the implicit one. So now, again, whatever is multiplying h, so 1/2 times this quantity in square brackets, that is your phi. So that's what we have here. So then you check for consistency. Let h equal 0. But here we have f of tn. And then yn plus 1, that will, as h goes to 0, that will converge to yn. So sure enough, you get f. So that method is also consistent. Questions up to this point? Okay. Now, there's one big picture left out when it comes to consistency. Right? You know how to show now that whatever one-step method is consistent. But that is not all we want to know about local truncation error. All we know right now is that local truncation error goes to 0 as h goes to 0. But we'd like to have an idea of the order of accuracy of the method. How rapidly does it go to 0 as h goes to 0? Does it behave like, is it order h, or h squared, or h to some other power? We don't know that yet. So now I'll show you an example. Okay, I have to duck out of this. Hold on. Okay. I have this in a text. I'm too lazy to write it out. Okay, I was unlazy enough to write it in the book. Okay. Now I'll reshare. Okay. So I have an example where local truncation error is worked out. I believe this is the right one. Yes, okay. So this is the same method. The midpoint this is a midpoint method. So the first method that I showed you. And this is just showing as consistent. But now I want to show an example of how you get the expression for local truncation error that will reveal the order of accuracy. Now this is a mess, as you can see, but I will take you through it. All right, so here, this first line is what the definition of local truncation error would give you. That you take your numerical method, you rewrite it in such a way that, okay, I'll go back to This is a method. But what you do is you rearrange it so everything's on one side set equal to 0. And divide by h. That's very important. You divide by h. That, again, that way it mirrors the ODE. Okay, so get back there. Okay. All right. So that's what we have here. Y prime, approximation of y prime minus f. So now what I need to do to get a handle on how big this can get or how rapidly it goes to 0 is Taylor expansion. So here I do Taylor expansion of y of tn plus 1 with center tn. And here are the first couple terms of that. So I take it out to the h squared term, and then I have something of order h cubed. That will be the next term. And then over here, okay. Oh, I'm missing a parenthesis, aren't I? Yes, I am. I think I already caught this in my large catalog of mistakes in this dang book. Okay, so I do a multivariable Taylor expansion of this function f, which is of 2 variables. So first, in the center is tn, y of tn. See, that's given here. So the first term is f of tn, y of tn, and there should be a right parenthesis here. Notice here I have f of tn, y of tn, and I have h over h. So this part is going to cancel with this. Then the next term of a multivariable Taylor expansion is df dt at the center times the change in t, which is h over 2 in this case. And then I have the term for y argument, df dy at the center times the change in y, which is h over 2 times f. And then the next terms in the multivariable Taylor expansion that I'm not including here would be of order h squared. All right. Now then what I do is I have here y double prime of tn. But y double prime is a derivative of f with respect to t. So by multivariable chain rule, I'm going to get df dt plus df dy dy dt, which is f. Because here we're using the fact that y is the exact solution. We have to take advantage of that knowledge in working this out. That's how we get the f out here. So now this fraction, this part, becomes this, and then I haven't done anything new down here. That's the same as it was up here. But now, it's a big old cancel fest. In fact, literally everything goes away, except for these big old terms. And here I have order h cubed over h, which is order h squared. Here I also have order h squared, so I have order h squared. So everything of order 1 or order h all cancel out. Now, if I had taken these Taylor expansions out a little further, then I could get a more specific expression for local truncation error. But it would be h squared times something. In this case, all I really care about is what is the order of accuracy. What are the first terms that don't cancel? Or lowest power in h that you get in this order h squared. Messy, I know. A lot of Taylor expansion and multivariable Taylor expansion to arrive at seeing if this is a higher order method than Euler's method, for instance. Questions about what happened here, the carnage? And I think I made it a homework problem. Okay. I want to check. Oh, let me back up a bit. Okay. 12.4. 1, 2, 3, 5, 7. One of the homework problems is to do the same kind of thing on a different method, a modified Euler method, which is also known as the explicit trapezoidal method, to show that it is, well, okay, you're supposed to find it a second order accurate. Oh, I already told you that. So have fun with that. But if you understand what happened here, you can model it after that. Same kind of terms that will come up. And if I could like to start, but I did not ask for a local truncation error of RK4.
Just verification.
Just show that it's consistent. It's a lot easier to do.
So we start by looking for phi.
Yeah, in this case, phi is large. But then you just do the substitution, let h equals 0, and it'll immediately collapse the.
Fun.
Yeah. What's kind of funny is that when I was an undergrad, like during my sophomore years, when I took basically this sequence, and the second semester was a class just on numerical methods for ODEs. And I had a friend who was a computer science major who was a bit ahead of me, and was doing some research that later I would join. And in that research, he was solving certain ODEs and using mathematical software to do that. And he talked about run a cutter method, and there's sort of mystique about it. I'd never heard of it. Like, oh wow, that sounds really cool. And then when I take that class and I see like 4/4 run cutter written out, like wow, you know. and now I'm looking back like, what was I on back then?
I think it sounds like a gang name or something.
Yeah, I guess. I don't know.
It's got a ring to it.
Yeah. But I guess he tried some like super powerful method for solving ODEs, but now I know about methods that are so much more powerful, and it's like hammer. Yeah, but the mystique is gone. Okay. All right. Let's see. Where am I at? Oops. Oh, okay. Not very far. Okay. All right. So that's one-step methods. How you show consistency. How you get an expression for local truncation error. So now I will shift to talking about consistency and local truncation error for multi-step methods. And the nice thing is multi-step methods, like one-step methods, also have a unified framework. Any multi-step method can be written in a certain form, this form. So that leads to a unified notion of local truncation error for these kind of methods. And here it is. So where we have values of y, you replace them with the exact solution, so y of t n plus 1 minus I. So notice the indices are the same. And then here we have f, you're substituting f of t, y of t, where you're going to use the same index for the t value. And like before, you rearrange the equation so everything's on one side so equal to 0, and you also divide by h. But there's one other wrinkle here. Notice I'm dividing by the sum of the betas. It's basically a normalization. Now, most multi-step methods, like Adams methods, for instance, the betas already sum to 1. But there's some methods where the way they're written doesn't do that, so that's why this factor is included. So, but it's just a normalization. Now, if I want to look at specifically Adams methods, for which we only have yn plus 1 yn, then this sum over h becomes this, similar to what we see in one-step methods. And then we just have this sum of betas. And here I've left this factor out because, as I just said, for Adams methods, the beta is always sum to 1. So this is local truncation error specifically for Adams methods. So the explicit Adams-Bashforth methods also the implicit Adams-Moulton methods. But now I can use my knowledge of how the betas are obtained, what they mean. Because this right here is to be written as an integral of f from Tn to Tn plus 1. So if I divide by h, I have 1 over h times this integral. And then this sum is also equal to 1 over h, but times this integral of this polynomial p. It's an interpolating polynomial that interpolates f at these times. So from Tn going on backwards, you also include Tn plus 1 if the method is implicit. So really, the local truncation error for an Adams method is an integral of f, or really it's 1 over h times the integral of f minus an integral of an interpolating polynomial for f. In other words, it's 1 over h times the integral of interpolation error. That's what it always is. And that's what I have here. So what I just said is written right here. Now, I've used this theorem from a text from this was covered last semester for polynomial interpolation error, and that is this integrand here. So applying this theorem to this interpolation gives you this. And then the 1 over h factor comes from a definition of local truncation error that is eventually divided by h. So then, if I use the fact that this product of linear factors will never change sign on the interval Tn to Tn plus 1, because one of the roots, the endpoint Tn is one of the roots, and then the other roots are outside the interval. In the implicit case, I would have a factor of s minus Tn plus 1. Again, that's an endpoint. None of these roots are in the interior of this interval, so this would never change sign. That allows me to apply the weighted mean value theorem for integrals. So this part, this involving this higher order derivative of f, I can pull out the integral. And then, if I make a u substitution in the integral, oh, you know what? Oh, I didn't write that down. Okay. Okay, I'll write it down here. Probably isn't text, but I'll put more observing here. So u is equal to Tn plus 1 minus t. Whoops. Tn plus 1 minus t all over h. And the reason for that is to map the interval Tn plus 1 to the interval 0 to 1. Then du is minus 1 over h dt. Now, the effect of that, this substitution is actually very important to get a handle on what the local truncation error is, because that means that, oh wait, not t, it should be s, because I have s here. I probably didn't need to do that, but I gotta be consistent. So this means that ds is minus h du. So that introduces a factor of h that will cancel out with this h. And then every single one of these factors, when I rewrite these factors in terms of u, each one of these introduces a factor of h. That gets pulled out here. And also minus 1. This is important because now I know what the order of accuracy is. So for an explicit method, Adams method, it's order h to the m. If it's an implicit method, there would be one more factor of h, so it would be h to the n plus 1. All right. Questions about what has happened here? I know it's a mess. So, interpolation error, make you use substitution, because it doesn't change sign, this gets pulled out, evaluate at an unknown point. And then, oh, you know what? That needs to be removed because I pulled it out. Okay. And yes, I really am going to check if I messed this up in the book. Oh, here I derived the truncation error a different way. Oh wait, it is here. Oh, okay, it is correct. All right. And then this is something that can be evaluated, and has been evaluated for certain cases anyway, so we know what those constants are. So you can look up local truncation error formulas for Adams methods of different orders. Okay. Now, actually, I'll show you here in the text for a general multi-step method. So this is a formula for local truncation error for a general multi-step method, not necessarily Adams, that I wrote down earlier. What I do there is I Taylor expand these and these. Although this is a derivative of y. So I don't do a multivariable Taylor expansion. These are, I express these as y prime. So then I do a single variable Taylor expansion throughout, because otherwise that would just be totally obnoxious. Okay. So this is what happens when I do that Taylor expansion. I just want to check here. As far as deciphering this is concerned. All right, so what I have here, this right here is Taylor expansion, just Taylor's theorem applied to y. And then here too, this is Taylor expanded, but thinking of this as y prime. And then I do some playing around with summation. Like here I have summation k equals 0 to infinity, but I make a k equals 1 to infinity. And therefore this k factorial becomes a k minus 1 factorial. Just so that I always have in both this summation and this summation, it's kth derivative of y. And my center is times tn plus 1 now. So after a whole lot of summation hocus pocus, this is what I get. So for my local truncation error. And the thing is, for a method to be consistent, I need this to go to 0 as h goes to 0. Well, that means that C0 had better be 0, because otherwise you get something over h. That'd be horrible. Some of these constants, like C1, C2, etc., also must be 0. Well, certainly C1 has to be 0 to have any hope of consistency. Because again, this h, one of these h's will cancel with this one. So, if I look at these constants, and here are their definitions right here. The method, I mean, C0 and C1 must go to 0 as h goes, in order to achieve consistency. Now, if additional CKs go to 0, then I have higher order accuracy. So what I can say is, to get order P accuracy, all of these need to be 0. And then this one would be non-zero. And then the order of accuracy is, the error is order h to the p. And then the local truncation error, simplifying as much as possible, is this, where all of these terms are 0 except starting at k equals p plus 1, we get something non-zero, and that's what's reflected here. And then we have additional terms here. Although I messed up in the book, this term needs to have a minus sign in it. So, whoops. Okay. Notice it depends on a higher order derivative of y. That'll become important for certain problems where what if this derivative is very large? Like if you have you might have an exponential like e to the minus at, where a is large. That function is tiny most of the time, but its derivative is very large because you're multiplying by a again and again. Yeah, so that can create a problem. Okay, so this is for general multi-step, that's local truncation error. So yeah, this is pretty ugly. And I'm honestly amazed that I didn't make a mistake until the very end. Still kicking myself over that. Okay. Alright. So that's actually all I have to say about consistency. Are there any questions about consistency? Okay, I'm going to check what homework problems I gave on consistency. Alright, so assigned 1, 2, 3, 4, 5. Okay, so as far as homework is stemming from this section. Okay, so the first one is show a local truncation error for a one-step method, and based on the example I gave, at least that one is humane. Well, okay, I'll let you touch that, but I tried anyway. Okay, show the method is consistent. And then the other problems. Oh, okay. Use these formulas to show that a 4-step Adams-Bashforth method really is 4th-order accurate. And then you would use this formula, don't get a minus. Well, I wouldn't take off because it was my mistake too, but to get the local truncation error. So for the method, you would have to write down first what are the alphas, what are the betas to plug in here. For the 4-step Adams-Bashforth method, it's 4th-order accurate, so that means that C0, C1, C2, C3, C4 must be 0, and then C5 would be non-zero. Okay, so tedious, but doable. Okay, then, okay, later problems I have to deal with. Okay, show the method is stable, and then number 7. Okay, show the method is convergence, second order accurate. Okay, now I have some time left. I want to be able to say at least a little something about stability, at least for one step. Okay, now, as I mentioned, a problem being well posed, unique solution in physics, system, and data, it can be guaranteed that the problem is well posed if your time derivative f satisfies a Lipschitz condition in y. We've seen Lipschitz conditions before, like for fixed point iteration. And this is found in like the existence uniqueness theorem. That if like another way of putting it is if f is differentiable, if the derivative of f with respect to y is well behaved and it can be bounded, that helps ensure a unique solution and well posedness. So, as I mentioned earlier, there's a relationship between well posedness for a problem and stability for a numerical method. So here's a general one-step method again. How do I define stability? This function, phi, must satisfy a Lipschitz condition. So, well posedness is if f is if the time derivative satisfies the Lipschitz condition, numerical method is well posed if the approximation of time derivative satisfies the Lipschitz condition in these variables, for yn and yn plus 1 both. So what that means is, because if I have two solutions, so two sets of initial data that give rise to two solutions, then the difference in solutions at time tn plus 1 is bounded by the difference in solutions at time tn plus h times the difference in these phi values. So, by requiring that phi is Lipschitz in both variables, what do I mean by that? Because I've shown you what it means to be Lipschitz continuous in one variable, and now we have two. This is what I mean. The difference in phi values must be bounded by one Lipschitz constant times the difference in one variable, plus a second Lipschitz constant times the difference in the other variable. So, suppose that this is, if we assume that this is true, that for whatever method you have, your phi does satisfy this, then what I can do is I can replace this with this in here. Sorry, I'm making sure it's still recording. Because I have less than or equal to already. And here I'm replacing this with an upper bound for it, so less than or equal will still apply. So now I have this difference in yn plus 1, less or equal to the difference in yn, plus these Lipschitz constants times differences of yn and yn plus 1. So, okay. I'm going to show you an intermediate step algebra-wise. Need to get to the right place. Okay, so I'm going to repeat this. And then I'll fill this in here, just so you can see where everything's coming from. Okay, so I have h multiplying both terms, so I gotta put that here. Okay. Now, here's what I do, algebra-wise. Here I have difference of yn plus 1s. Here too I have a difference of yn plus 1s. So I'm going to take this term and move it over here. So now I'm going to have on the left side 1 minus HL2 times this. Over here on the right side, this is still here. I'm going to have 1 plus HL1 times the difference in YNs. And then I divide. So this is what I have. So difference of y plus 1 is less than or equal to this scaling factor times the difference in YNs. So this is what happens over the course of one time step. Whatever deviation we've had up to time tn can get amplified by this to get a difference of solutions in the next time step. And now I'd like to get a handle on how big this can get. So first I'm going to rearrange it. I want to write it as 1 plus something. And that's what I do here. And then I'm going to make an assumption about h, the time step h. Because I want this to be positive. I don't want to worry about dividing by 0. So in other words, that's going to limit what h's I can consider. H needs to be sufficiently small. So I will assume that h is less than or equal to h naught, where h naught is this. So that guarantees there's no division by 0 issue. And now I have this. But then what I can do is I can apply this repeatedly, because the difference in y plus time tn plus 1 is bounded by this constant factor times the difference at time tn. So if I apply this repeatedly, the difference at time tn is less or equal to this factor raised to the n power times the difference in the initial data. This is the first two terms of an exponential, a Taylor series. So I bound it above by an exponential. That's a very crude bound, but it works. And the reason why that helps is because it's raised to the n power, and h times n is the difference in time values. So now I can say that the difference at time tn is bounded by the difference in initial data times this scaling factor that is independent of h. That's the important thing. So no matter, as long as h is sufficiently small, as h is going to 0, the difference, whatever difference you have in initial data is amplified, but in a reasonable way. The growth it's controlled growth. That's the key. That's what stability is about. Controlled growth. That does not continue mushrooming without bound as h goes to 0. So the method is stable. Now, well, I have this constant k here, and I did not define at all what it means. Okay, I need to show you that, don't I? It's in the book. I love that I can always say it. It's in the book. All my professors who wrote books did the same thing. Okay. In the original definition of stability, yes. The original definition of stability is that the solution is bounded by some constant k times this. And now we have to handle what the constant k can be. And as long as it's independent of h, that's all we need. So in this example, sorry, this is looking a little different than what I have here. Oh, I used one unified Lipschitz constant for both in here. But anyway, to correct what's in the notes, k is not this, but exponential of this. I have to include that. Okay, now it's correct. So anytime you can establish that the error, the difference at time tn is bounded by a constant independent of h times the difference in initial data, whatever constant it is, that's a constant k from the definition of stability. That is definition. Sorry, I'm jumping all over the place here. You need to pause the video. Definition 12.4. Okay. Okay. So, because this definition of stability, it's difficult to show this directly for a given time-stepping method. But now you don't have to. All you got to do is show that your function phi for your one-step method satisfies the Lipschitz condition in yn and yn plus 1. And now, from what I've just shown you, this is guaranteed. So now I can focus on that. Are any questions about what happened here, though? All right, here's an example of how you would do this for a specific method. midpoint method. So here's your midpoint method. So you got to show that here's your function phi for the midpoint method. You got to show that it satisfies the Lipschitz condition in y. And you don't have, in this argument, you don't have y plus 1 as an argument, because this is an explicit method. So that helps. So let's take a look at how this works. So you evaluate phi at two different values of yn arguments, y2, y1. And we're assuming that f satisfies the Lipschitz constant to show that phi also satisfies the Lipschitz. We assume f satisfies the Lipschitz condition to show that phi satisfies the Lipschitz condition. So we're piggybacking off the Lipschitz constant of f. So here we have this difference in f values. And so this is, by the Lipschitz condition for f, we know that this is bounded by f's Lipschitz constant times the difference of this argument and this argument. So we have that here. And now I can break this up. So I have L times the difference in y's plus HL over 2 times the difference of these f values. But again, here I apply the Lipschitz condition for f a second time. That this difference is bounded by L times y2 minus y1. So now I get an L squared in here. So this is a Lipschitz constant for phi. And what we see is related to the Lipschitz constant for f. Now, it does depend on h. So we need to assume that h is bounded by some h naught, where h naught is defined as I did earlier. And then you have stability. All right. So questions about that? So to summarize, one-step methods. You find your phi function and define this one-step method. Let plug in h equals 0, show that you get f, and then it's consistent. You can take the definition of local truncation error, which is approximation of y prime minus phi. Then you do Taylor expansion all over the place to get a handle on what the order of accuracy is for a one-step method. So that's consistency. For stability, you assume that f from the ODE satisfies the Lipschitz condition, show that phi also satisfies the Lipschitz condition using f's condition. That shows stability. For multi-step methods, I haven't talked about stability yet. I'll do that on Monday. For consistency, there is a formula for local truncation error. It's the same definition of local truncation error, specialized to multi-step methods. But now we have criteria that's constants that are defined in terms of the alpha and beta coefficients of a multi-step method, and you can check which ones of those are 0 to find the order of accuracy of your multi-step method. But for Adams methods, it's already been firmly established what the order of accuracy is. For an m-step Adams-Bashforth method is HVM, or m-step implicit Adams-Boltzmann method is HVM plus 1. So these are things you can do to check the properties of your method, and then I will continue with that on Monday, starting with stability for multi-step methods, which thankfully is not too much of a pain. but I think we've all suffered enough. It's still hot in here. But in the last few minutes, if anyone wants to shout out any homework questions, certainly you're welcome to do so. Okay. till Monday.